You are welcome to our lecture number 3 on Cmen723, which is basic electronics. This lecture is going to be on power supply circuits. What we need to know is the electricity we receive from distribution companies, it is AC, that is, it is alternating current. The voltage is not stable, it keeps on changing between positive maximum and positive minimum. But most of our electronic systems, our radio, television, computers, everything, they require a DC voltage. So there is need for a circuit that will be designed to take that AC and change it into equivalent DC so that these electronics appliances can use it. And in the process of doing that, we have 4 steps. The first one is transformation. The voltage that comes from the main supply is around 220 to 240. So we have to use a step down transformer to reduce it to 10, 12, 15, 20, depending on the voltage requirement in DC system. The next thing is rectification, that is to change it from flowing in 2 directions to now flow in 1 direction. The next thing is filtering, that is removing the what we call ripples in the rectified signal so that it can be somehow steady DC. And the last one is filtration or filtering. Regulation. We use a circuit or component we call regulators. Its function is to keep our output DC voltage constant regardless to the changes taking place in the original AC signal. And let us follow it and see. In our previous class, we have seen the applications of what? A diode. And we have seen that diode can be used to change a signal flowing in 2 directions to now flow in only 1 direction. If you can remember, this is the waveform, a graph of what? AC signal. So if you pass it through a rectifier, which is mainly made using a diode, we can have a half wave rectifier and the full wave, if you can remember. So now if it passes through this rectifier, instead of flowing in 2 directions like this, it will now be flowing in only 1 direction. So the circuit responsible for changing this to this is what we call a rectifier. And the rectifier, as we have seen in the other class, they are of 2 types. We have what we call half-wave rectifier, which allows only one part of the alternating signal to pass and cut the other part. If you connect your diode like this, that is anode here in contact with the transformer and the cathode at the other end, your AC input, this one, will now be only flowing in the positive direction. Anything below here, these dotted lines, it means they have been cut. They cannot pass. So we maintain only this positive half, and that is why we call it half-wave rectifier. But if you change the orientation of your diode, that is your cathode now in contact with the transformer, and the other end, which is the anode to the load, we will be allowing the negative component to pass from here, and all the positive, they will be cut off. This dotted means they are not allowed to pass. So from that, what is the average output voltage for a half-wave rectifier? If you want to get it, we use this formula. V average is equal to 1 over T, where T is the time to make a complete cycle, that's the period. Integral of V max, that's the maximum alternating signal from my AC component. Sine omega T, where omega is what we call the angular frequency, it is equal to 2 pi over T, where T is the period. So the aim of this is not to teach ourselves mathematics. That is why if we now remove this omega here and put this, my equation will become here. So I'll finally see, after integrating this one, I will get this expression, that is the average is equal to maximum over pi. And you know pi is 3.142, something like that. So if you take that, it will give you 0.318 volt maximum. That is the average output voltage, the DC, will be around 31.8% of the maximum. Why? Because already 1/2 is already cut up. So the 50% is the one that will finally give something like this. So the second type is also in part of my last lecture, is a full wave rectifier. And if you look at this one, instead of using a single diode, I'm using 2. This is D1, this is D2. So and I have a center type transformer. This is my input AC signal. When this one comes, the positive part, it will pass through this diode number 1, and it is the one I am having here. Then when this one is conducting while this one is cut off, this negative part will be conducted by the second diode D2, but it will conduct it in the positive direction. So as you can see, this one is what? Both sides, positive and negative, but after passing through this full wave rectifier, it is now flowing in only one direction. So in this case, we didn't abandon or we didn't destroy any part of our signal. All the two parts are allowed to pass. So with that, my output should be something like this. That is, instead of being bidirectional, that is flowing in positive and negative, it is now flowing in only one direction, the positive direction. And up to now, this signal, we cannot call it DC because it is also alternating. You have to pass this one through what we call a filter, so that it will reduce the alternating, the variation here, so that it can averagely be close to this DC, which is constant with time. And in this case, the average voltage, the maximum, I mean the RMS value or the average voltage is equal to 2 times that of the half wave. So if you multiply this, 0.308 or 308 times 2 will give you 0.616 times what? The maximum AC voltage, which means here I have 61.6% because I'm allowing the two parts to pass through the rectifier. Now after doing that, as we have seen, this signal, it is not constant, but it reach maximum and come back to 0, though it is not passing through the negative part, but still it is not a DC. We call this one unidirectional output. But what we want to achieve is something like this. That is the signal to be constant like this. We want it to be stable like this. That is, time is changing, but it is fixed. So if you want to do that, you have to employ the help of what we call a filter. And the simplest form of filter is a capacitor filter. Here is my AC input, and this is my rectifier, and it is the rectifier that will give us this output as we have seen. Now the output that keeps on changing maximum to 0, maximum to 0, we now pass it through a capacitor. If you can remember, a capacitor can store charges. So what happens is this: whenever the signal is rising from 0 to maximum, this capacitor will be storing charge. When it is trying to fall from maximum to 0, the capacitor will now start releasing the stored energy, and for this reason it will not allow it to go to 0 because it is producing output to counter that. In the second half cycle, when it is rising to maximum, the capacitor will be charging. When trying to fall down, the capacitor will release its energy, so that you can see instead of rising from maximum to 0, maximum to 0, it will now be somehow constant because of the energy the capacitor is releasing. So the ripple is this amount of variation because it is not steady, it is not a straight line, just like the other one we have seen. So the value of this voltage, that is the ripple voltage, is equal to IDC, that is the DC current, all over 4√3 of what? FC, where F is my frequency of the system and C is the capacitance of the capacitor, which is given in microfarads. Now, what is the value of this DC current? The DC current is equal to the DC voltage all over the load resistance. Okay, this is the ripple voltage, which is given by IDC all over 4√3 FC, and my IDC, that's the DC current, is given by VDC all over RL, where RL is the resistance of the load. Now the capacitance C is already defined, and the V is the average voltage as we have seen. RL, I have already defined it as load resistance. So delta V, that is change in voltage, is equal to V minus V input minimum. Now this is another type of a filter circuit. This is the first one we have seen, where we are using only one capacitor. So now we added resistor and capacitor, and that is why we call this one RC filter. And if you wish, we can call it bisection filter, because capacitor, and this just like the shape of a pie. And how do we get this one? We additional resistor and capacitor in this connection, as we have seen. And the function of this one is, this one will filter part of what it can, and this one is to addition or to add more attenuation, that's more reduction to the ripple voltage. Now the next thing is the voltage regulation, because we have seen that transformation, rectification, filter, and then voltage regulator. The function of voltage regulator is to keep the output voltage constant even when there are changes in the input voltage, because sometimes the supply voltage from the PSCN can be 220, 210, 190, something like this. So the function of this regulator is to make sure if we need 5 volt here, it will remain regardless to what is happening here. And how is that achieved? It is achieved using a transistor with a capacitor and what we call a Zener diode. This is not the ordinary diode we know. And how does this one help to maintain constant output voltage regardless to the changes in the input? What happens is that whenever the source voltage goes down, the voltage between the base and the emitter, this is the base and this is the emitter of this circuit, will now increase as a result of the fixed reference voltage we have with this Zener diode, so that whatever happens, the output from the emitter of this transistor Q1 should be constant. Therefore, there is no any change. Now, apart from that, we also have a 3-terminal regulator, which are normally given as 78XS or 79XS series. The 78XS, they are the ones that will give you positive DC voltage, 5 volt, 9 volt, 12 volt, 15, and the rest. And the 79XS, they are the ones that will give you negative voltage, and they are fabricated in form of integrated circuit, that is IC. The ones that are 78XS and 79XS, I have already said they have 3 terminals. We are going to see the figure very soon. 78XS, they are the ones for the positive voltages, and 79 for the negative voltages, where this XS is the voltage we want to get. For instance, if you have 7805, it means it will give you positive 5 volt. 7806, it will give you positive 6 volt. 7809, it will give you positive 9 volt, and 7812 will give you positive 12 volt. Likewise, 7905, 06, 09, and the 12, they are the ones that will be giving you negative voltages respectively. Now, the circuit, I said you are going to see this. This is the pictorial view of the regulator. This is pin 1, pin 2, and pin 3. Pin 1 is the input, and the pin 2 is the common connection between the input and the output, while the pin 3 is the output. And internally, this is the circuit that is contained in this IC. We have a pass transistor, and we have thermal shutdown and current limiting circuit. Its function is to make sure that whenever the temperature is very high, it will switch off the circuit, and it is limiting the amount of current, because the current mostly is the one responsible for increasing the heat. And here we have 2 resistors, R1 and R2, and they are connected in what we call the potential divider. And this is my operational amplifier. Its function is to compare the variable voltage here and the reference voltage. When the two are the same, then the error should be equal to 0, and the output will be maintained. But whenever they are different between the reference and this, it will now supply this one so that it will adjust this to maintain it at the fixed value. The VE, that is the difference, that's the error between the reference and the variable, is given by this formula. As I told you, R1 and R2 are connected in potential divider mode. So my BE, the error, is equal to R1 all over R1 plus R2 times V0. So the output voltage, the V0, is given by 1 plus R2 over R1, everything times the reference voltage. So the next thing is, from the beginning of this lecture, I told you for us to design a power supply circuit, we need the level of transformer, the level of rectification, we need the level of what? Filtration, and finally the regulation. And this is the last thing we have just discussed, regulator, and it is connected at the end. After transformer, we rectify it, we filter it, and finally we use our regulator here. And we have seen that it has 3 pins. There is input, there is output, and there is a common terminal. So one important thing we need to know is that these regulators we have seen 78 families and 79 families, they can ranging from 0.7 amperes up to 1.5 amperes according to the manufacturer's specification. So whenever you want to supply a current in this range, you can use this family. When it is more than that, then we have other regulators available. So when they are used in a system with a high load current, we attach what we call the heat sink. It is a metal, mostly aluminum. We connect it to the body of that IC so that whichever heat is generated, it will now be absorbing it and dissipating it to the outside wall. So the next thing is these families we have seen, they have range of the voltage. Like 7805 can take a voltage from 7 volts minimum to 25 maximum, and 7806 from 8 volts to 25 also. 7809 will take from 10.5 to 25 also. Then we have 7810, this is the range of the voltage. 7812, that's for 12 volt, this is the range from 14.5 to this. And 7815, that is for 15 voltage, 15 volt, it can take minimum of 17.5 to 30, and then 18 also, and the last one 30. So wherever you want to use any design, you have to remember these ranges, the minimum and the maximum. And for us to bring out this clearly, let us give a sample question. We say design a power supply circuit with a center tap transformer with a regulator that maintains 12 volt, which means we need a regulator of 12 volt, that's 7812 DC output, into a load that requires this range of current from 100 milliampere up to 400 milliampere. And we are told that the AC voltage from the source is 220 and the frequency is 50 from the mains, and the resistance that will be serving as RL, that is the load resistance, is given by 100 ohm. Now in our design, this is what we start doing. Since it is 12 volt, we are going to use 7812 regulator as we have seen. And if you go back to that table, the minimum voltage for 7812 is 14.5 and the maximum is 30 from that table we have seen above. And now we want to find the average input voltage, which is summation of the maximum and minimum over 2. That's 14.5 plus 30 over 2 will give us 22.25 volts. Now the peak input voltage, B peak, is equal to the supply 220 times root 2. If you multiply it, it will give you 312.4 volts. And since we are using center tap transformers, it is stated in the equation and in the question, we need each half of the section to have this. That is B peak over 2, this value 312.4 over 2. Each side should carry 156.2 volts. Now from here we can find the number of turns in our transformer, because you have seen the first thing in power supply is to get a transformer that will reduce your high AC voltage to the low. So now we are going to use this, which is the half voltage in each of the side of the transformer, which is 156.2 all over this average value I have gotten 22.25. Approximately I need 7 as the turns ratio. That is the number of turns in the primary compared to the secondary, it will be 7. That is, the primary is 7 times the secondary, because you know the more the number of turns, the more the voltage. So the primary, which has 220, will have higher, 7 times that of the secondary. Now the next thing we'll do in this design is to calculate our capacitor, and the formula of this capacitor is given by V over delta B FP RL, where this FP, that is the total frequency, is equal to 2 times the supply. We are told that it's 50 hertz. 2 times 50 will give me 100 volt, 100 hertz. And I have already calculated my average voltage here, and delta V is equal to the difference between the V and the minimum. That is 22.25, which we calculated here, minus the minimum for this regulator 7812, the minimum is 14.5 as given in the circuit. So my delta V is equal to 7.75 volts. Now my load resistance, it has already been given in the question as 100 ohm. So I will now substitute my V. I'll put this average value I got all over my delta V is 7.75, and my F P, that's the frequency, is 2 times 50, which is 100, and my RL is given as 100. If you simplify everything, it will give you 2.78 times 10 to the power minus 4, approximately 287 microfarad. And this is the design. As you can see from here, is just to get our average value of the voltage, to know the number of, the voltage in section of the center tap transformer. Using that, we now get our number of turns in our transformer. Then we calculate the filter capacitor as we have seen here. So this is the end of this lecture, ladies and gentlemen. Thank you very much. I advise you as usual to watch this over and over again. Definitely it will be something very helpful to you. Till we meet in our next lecture. Thank you very much.